Basically, this is a maybe tutorial or a seminar about DDoS mitigation and DDoS problem. So the main outcome from the presentation is, I'll put it out straight, is that I hate Mondays and I'm not a morning person. But we'll see. The tutorial will be 1.5 hours long, and I've asked the host to shut the door with a key, so you wouldn't escape. Let's start now with, oh yeah, I have a clicker. Nice. So, oh, only it doesn't work, sorry. Let's start first with some ancient history, as usual. So, because it helps to understand the problem. First, denial of service attacks were seen just about the end of the previous century. In about 5 years, they began to be a serious problem for ISPs and other network entities. Like data centers or end users. In 2015, Microsoft finally addressed long-term concerns about the security of Microsoft Windows and other products with software development lifecycle methodology, which is like a methodology towards software secure code development. Among all the published concepts within this methodology, there was the STRIDE model. STRIDE model is a threat classification model which provided a mnemonic for security threats in 6 categories. The STRIDE was initially created as part of the process of threat modeling. STRIDE is a model of threats used to help to reason and find threats to a system. It's used in conjunction with a model of the target system that can be constructed in parallel, and it includes a full breakdown of processes, data flows, and trust boundaries. It's described on the Wikipedia. I won't go into any detail, but today it's often used by security guys to help answer the question, what can go wrong in the system we are working on? As you can see, there's a denial of service in this model at the 5th place in the list. However, Microsoft security experts meant something different here. So most of you have probably heard that there's a distributed denial of service attack on one hand, and you know, just denial of service, like not distributed. What is the difference? Traditional understanding of the difference was like this: if a DOS attack comes from multiple sources, then it's distributed. Unfortunately, no one bothered to strictly define what the word source means here. The source in this context may be, for example, a computer, like a machine. So if it's multiple machines in the attack, say 2 or maybe 3, then it's distributed. Maybe number 3 is too small, then 4. A question arises immediately. If it's a machine, should it be a physical machine or a virtual instance counts? Do root or Linux containers count then? What if there are 2 virtual machines under a single hypervisor? And what if they occasionally migrate to another physical server, which happens frequently in the cloud? What if there are multiple IP addresses assigned to a virtual machine from different IP prefixes, and how is it then different from a distributed attack from a victim's point of view? If source, maybe it's an IP address, Then it's possible to spoof a single IP source traffic from a number of network attached nodes, say thousands, thus utilizing a bandwidth greatly exceeding capabilities of a long handling server. Once again, how is it then different from a distributed attack from a victim's point of view? The idea about telling apart DOS and DDoS based on the count of the source machines dates back to the beginning of the century when computational resources, including networking, of clients and servers were comparable and single-sourced DOS attacks were more or less common. However, these days, in regards to the mitigation, of course, it's almost useless and almost impossible in practice to tell apart DOS and DDoS attacks. With this in mind, we prefer to use a different approach. A DOS attack, like not distributed, is basically when an attacker generates a specifically crafted packet to exploit a vulnerability in a packet handling code. Like ping of death, like null pointer reference somewhere in a packet handling code. This is, by the way, what was meant by denial of service in the Stride model. On the other hand, a DDoS attack, a distributed one, is a computational resource exhaustion, no matter the size of the attack. Computational resources include memory, processor time, network bandwidth, and others. But basically, all the resources are finite, and if there's an attack which makes use of some resource and makes an exhaustion possible, then it is a DDoS attack, no matter the count of the source machines. The basic idea behind Stride and other approaches is risk management, risk modeling, and risk assessment. Basically, you enumerate possible threats, analyze them, and then manage to avoid being hurt. However, assessing threats isn't easy. People are often afraid of scary things, scary but unlikely risks, not giving enough attention to real threats. So there are tools which are useful for addressing risks. One of them, it's simple, is a probability impact matrix. Here's how it works. On the vertical x, there's a probability of an event, and on the horizontal x, there's the incident severity, how harmful the event would be in case it happens, how much of a destruction will it cause, and how much it all would cost. Rare and trivial threats in this corner are the ones you most of the time don't care about. Severe and likely risks in this corner are the ones you handle first. Then there's a large field between those where you set priorities, plan, and manage. A DDoS, like distributed DDoS attack for an average internet resource, is something which is totally dangerous. The idea is that basically, if a weakness in your system is discovered, the attacker knows your IP address, so handling an attack may imply changing IP addresses, changing ISPs. In case of a small data center, maybe even relocating. Because a cloud may not help you because an attacker knows the origin IP address. So it's totally dangerous. However, for an average internet resource, it's sort of unlikely to happen. So good news. There are, however, bad news. Cases when a DDoS attack becomes much more likely to happen. Let's consider the motivation of an attacker. This is not exhaustive, but not a fully complete, but almost complete list of the reasons why attackers issue DDoS attacks. It ranges from just fun. Yes, it happens because it's funny to bring a large and famous internet resource down. To blackmail, usual thing. It's the simplest way to, by the way, to make money out of a large botnet, because you can do other things like spamming or identity theft or anything else, but making DDoS attacks possible is the simplest way of actually getting some money out of a botnet via blackmailing. Then it's maybe self-promotion. If you have a large botnet, you want to be heard, you want more customers, and you want to be known across the community. Let's call it community, I don't know. So next is, of course, political statement, revenge, but probably one of the main reasons is market competition. It's like widespread in the Pacific region and a lot of other countries, because like if you're like, if there are two competitors, yes, and there is a like Google search. If a resource is down for a while, it will go down in the Google search results either. So this is one way to make a competitor look less attractive than an attacker, an attacker's company. There are other reasons, like customers will be disappointed by the resource going down, etc. So market competition is one of the main reasons to bring websites and network resources down. In case of financial organizations and more recently blockchain-related companies, diverting attention is also a case when a DDoS attack is meant to just cover some other cyber attack, like a theft or other attacks, just to make sure that a network department and security department of a company will focus on precisely the handling a DDoS attack and won't notice the theft in a few days. And last but not the least is preventing access to compromising information in case it's a newspaper which publishes information about something going on. Then those who are mentioned in this article may want this information to be absent from the internet. If anything in this list applies to a network resource or its dependencies, like a DNS server providing services to a newspaper, say, then the probability of a DDoS attack becomes higher. Not everything in this list is controllable, however, but something is. Say, it's hard to predict somebody going to blackmail or just make a joke out of a network resource, but the rest of it is more or less predictable for a network resource and for providers of network facilities for a network resource if they follow like market situation, price situation, and others. So it's more or less controllable. You just need to put some effort in it. So with that in mind, let's now talk about classification and categorization of DDoS attacks. Here is a list from Wikipedia. It's longer than that. I believe if we'll start just counting names, it will contain about 100 bullet points. I think death by bullet point is exactly a description of this possible slide, so I won't go this way, because like in case a new attack is discovered, you need to expand this. And if in case you are building a solution or buying a solution, how do you know if future threats will be addressed by this solution? So basically, a DDoS attack is a network resource exhaustion. A computer network, as of today, we are not speaking about future protocols like QUIC, which combines a lot like transport and encryption and security in one piece, but now a computer network consists of layers. A network resource is not available to users when at least one network layer fails to provide service, fails to deliver its function to a user. With this in mind, a DDoS attack can be attributed to a network layer, not like layer 3, but network layer which it affects. This is basically the model of DDoS attacks. We'll go into detail. Wait for a minute. But basically, we start with low layers when only which are responsible in terms of like real resource just for bandwidth. And when we go up, it's TCP or TLS edge cases, because there's a complex finite automata which can be used to exhaust the memory or processor time, processor resource. And on the layer 7, there are different application-specific bottlenecks we'll discuss later. Having layer 2 in this model is important because it highlights the difference. When we speak of layer 2 attacks, we don't mean like ARP-based flooding. Likewise, when we speak of DNS amplification, we don't label it with layer 7. DNS is a layer 7 protocol, yes, but the effects of an amplification attacks are obvious even on lower layers of OSI model. There's a long list of attacks related to low layers. That's mostly volumetric flood. That's UDP flood, that's scene flood in some cases. There are other attacks, but the main thing is probably amplification. What's the amplification DDoS attack? In a nutshell, it happens in such way that most servers on the internet serve data to clients, not vice versa, but they serve data to clients, and they usually send more data to a client than they receive from them. This is okay for TCP-based servers, as the TCP protocol has a built-in mechanism called triple-way handshake for verifying the remote, which can be used to verify the remote IP address of a client. In a way not built into a protocol, but discovered by Daniel J. Bernstein back 20 years ago, I guess. However, there is no such mechanism present or built in the other transport protocol, UDP. Each author of a UDP-based protocol must design their own handshake, and sometimes they just omit this during a design phase. Thus, an attacker is able to impersonate a victim by spoofing source IP address of a victim and to send a request for a large portion of data on behalf of a victim. An attacker will generate, say, 1 gigabit of requests, but the victim will receive, say, 30 gigabit of responses, which may impose serious consequences for the link congestion. There's a long list of protocols vulnerable to amplification. Those are mostly obsolete protocols like Routing Information Protocol version 1. It's too old. But also like gaming industry is heavily contributing to that. Like recently, like Quake or Steam protocol are also possible it's also possible to amplify the traffic using those gaming protocols. Yes. As it's mostly obsolete servers, eventually they get either updated or replaced with new ones or just trashed. Thus, the amount of amplifiers, as measured by Curator Radar, shows steadily downtrend. However, once in a while, a new vulnerable protocol is discovered, and the number of amplifiers on the internet just skyrockets at the moment and starts to decline again. One of most important things about amplification is the term called amplification factor. The amplification factor is how much data you can get in return towards the victim from an amplifying server compared to the size of a spoofed request. There's also a stable downtrend in terms of an amplification power available on the internet. The factor is different for each protocol. It's higher for SSDP or NTP, and NTP is like 10 times more powerful than LDAP. Most amplification attacks are easy to fight with, as the source UDP port is fixed. So at the first glance, it seems like you can use a simple bit mask to track down and filter packets which come from a typical amplification port, like 123 in case of NTP, or 53 in case of DNS. Moreover, there is a mechanism you can use to actually order that filtering from your upstream network service provider, which is called flow specification rules, RFC 5575. Using flow specification, flow spec, you can notify your upstream provider that you don't want or need to receive, say, packets from a particular UDP port, which comes in handy when you face a powerful amplification attack. However, I'm sort of tired of saying however, but I'll continue. There are at least two major problems with flow specification for that particular task. The first one is ICMP amplification. If you use flow spec to drop all the ICMP packets, this will have serious consequences for other protocols and network interoperability. And like if you open a man page for IP tables or IP tables extensions now, you'll easily see that those sysadmins or network operators which drop ICMP packets are described as brain dead there. But the other problem, except for ICMP, is when an amplification attack doesn't actually have a fixed UDP port. That's a case, for example, of BitTorrent. There's a huge research towards BitTorrent-based amplification attacks. And we'll go into some detail when an amplification attack doesn't actually have a fixed UDP port. There's also another problem with amplification. Let's consider a recent example. This is a story from this February about memcached. So memcached, who have heard about it? Please raise your hand. Oh, great. So basically, memcached is a database frequently used by web developers. It's an in-memory key value store, which can be used to put and then retrieve values for specific keys. It's often used as a fast cache, hence the name. And long time ago, memcached authors made a huge mistake. They made memcached listen on all the network interfaces, including externally facing ones by default. There's a lot of machines on the internet with port 11211 open, UDP. And this port is memcached ASCII protocol listener. The basic ASCII protocol was meant to be used on a loopback interface only, or in a local secure network at most. However, it's exposed to the internet and it doesn't do any authentication. It's known for long for its weaknesses. 4 years ago, Ivan Novikov from Valarm has discovered numerous methods to exploit memcached ASCII protocol and to inject an arbitrary data in it. In the memory of a memcached instance, there's a presentation on Black Hat USA about it. And in November 2017, security researchers Shengbao Kai, Zhang Lu, and Li Fu have discovered a way for an attacker to use this ASCII protocol to send large portion of data from memcached memory towards a victim. This is a good and handy example of how an amplification attack works. Let's look into that. Here's the code. This is all which is required to inject a value of an arbitrary size, like a few megabits, in a memory of a vulnerable memcached instance available under the name reflector.example.com. So this Python code snippet is all you should do to inject a value of an arbitrary size. And for the sake of DDoS amplification, this snippet should be run only once. Then an attacker needs to send packets toward that vulnerable server with victim's source IP address and a proper payload which memcache will treat as a correct request. So back to the previous slide. The key is A, and here is the correct payload of an amplification attack. You can spot a key called A and a method which is called get. So to retrieve a value. The value is reusable. Yes, this is a correct payload. This is all you need to send in a application layer place, and you only need to do it with a spoofed IP address, and I won't tell you how you do this, but it's easy to find out. What's even more convenient for web developers and was completely disastrous for some network operators, the gets method accepts multiple arguments at once and allows to repeat those values. So here is what you can do to send the value of A 5 times in a row, multiplying the attack traffic 5 times, or 10 times, or 100. No more than 100 because you have an finite, you have MTU size, so it's not possible like to do it 1,000 times, because the data will be split between packets, and the attacker won't get a lot from this sort of an attack, but you can do it a few hundred times. By default, like in Red Hat or CentOS, memcached listens on all network interfaces with TCP and UDP transport enabled, and no authentication is required to access memcached. The service has to be manually enabled, and the default firewall configuration doesn't allow remote access. And there's also Linux, which most of sysadmins just switch off at some point. So most of the time we still see memcached instance exposed to the internet. Also there's Zimbra and some other software which uses memcached and expose it to the internet, not caring about firewall configuration or patching it or anything. So basically, as we've discussed before, the amplification factor is how much data you can get in return compared to the size of the original request. So our previous champion was NTP with amplification factor as high as 557 by the data coming from NIST. There's a long research about how this is measured. This is an average. But for NTP, it was supposed to be about 5 or 600. However, for the memcached amplification, in theory, this factor would be like millions. However, in practice, all the packets of a response aren't sent at once. And in practice, we've seen an amplification factor close to 9 or 10,000, still 20 times NTP does. Amplification texts were meant, for a long time, they were meant to be more or less under control because of flow spec and other measures. However, as practice shows, they are something not to underestimate. So, there's a snippet posted by Job Snyders from NTT. Here is a link. How you can rate limit, not drop completely because it contradicts with network neutrality, yeah? So you can't just drop traffic coming to or from a particular network port, but you can rate limit it. And here is how you can rate limit amplification sensitive ports. The memcached port 11211 is here just as an example. This is port iOS XR. I won't go deep into that. The slides are available on the CSNOC meeting website. But basically, you just define a policy map which you then apply to your customers' interfaces. For recently developed network protocols, UDP-based, it's like a must to implement some measures against possible amplification threat. Take Quick, which is a new and heavily developed concept from IETF. In case of Quick, the initial handshake packet is padded to 1,000 and almost 300 bytes to make sure that it's actually padded to that size. So the initial packet coming from client does not contain this amount of data. However, it just to make sure that the server, in case the server will reply with a large portion of data, it won't cause amplification because client is also sending a lot of data. Also, Quick has built-in source address validation technique, which happens at the earliest phase of handshake to make sure that no data will go through that server to a third party. This is just one, but more or less complex example of a volumetric attack. It's not limited to amplification only. An attacker can also generate random UDP flood or DNS flood or anything else, but amplification is probably the most widespread one. Another example of famous volumetric attacks is IoT attacks, which are known for long. It's I believe, yes, as early as 2014 with a lizard stressor, which started using IoT for DDoS attacks. Then 1 year later, small office and home office routers became a persistent threat for malware. And again, 1 year later, Mirai appeared. Mirai in September and October of 2016 was a tool which was used to generate like 1 terabit of attacks towards OVH or Google or Akamai, or basically a blog of one security researcher. After that, it was supposed that it was because an attacker was pursued by Interpol or FBI, and they didn't want to this code to be discovered on their computers, so they just uploaded it to a random forum, and it ended on GitHub. So the source code of Mirai was available on GitHub for a long time. It's still available there. There's, I believe, about like 100 or maybe even thousands of forks, and like in the previous year, we've seen a lot of those forks in the wild. They are called differently. There's also a long list. There's, I believe, also hundreds of IoT botnets now, which is sort of fortunate because a camera, as given the design of original malware, is not able to participate in different botnets at once. So when it was Mirai and only Mirai, covering all the cameras in the world, it was possible to generate like terabits of attacks, but with this power splitting across hundreds of botnets, the average power of one botnet is a lot lower. However, there's another threat related to IoT. We'll discuss it later. So, a low-level attack may also can also affect the infrastructure of network-connected entity. So not only the end web server, but also the infrastructure before it, firewalls, anything in a network which goes with a state, like a state enabled firewall, connection tracking firewall. So it's not only a bandwidth, but it's also related to the infrastructure, the ability to transmit packets. And towards a mitigation of this from a victim's perspective, you probably want an anycast network because, as it's widely believed, I've heard this multiple times, and I don't have anything against this proposal, that it's almost impossible on the internet to handle more than 500 gigabits at a single point. I believe Cloudflare has posted this number. So basically, you want an anycast network with nodes in different regions of the world, connected to different ISPs or internet exchanges, with enough inspection power to handle complicated attacks with a correct payload. Also, you probably want to do some inventory management to drop traffic vectors you don't want to see, like UDP coming towards an HTTP server. You also want to probably rate limit the traffic which is less important, like, I don't know, maybe mailing in case of a web server. And also, you want to do challenges and handshakes. We'll discuss it when we'll go towards the transport layer. From an ISP's view, the scope of an ISP is limited to bandwidth-related attacks, and it's possible to apply simple heuristics against typical attacks like amplification. For anything else, if you are not doing DDoS protection like for money, you probably want to use remote triggered black hole to force your customer to take care of the attack themselves. So let's go to the next layer, or even 3 layers. The OSI model is not great when you go to recent protocols, but let's attribute a TLS to layer 5 and 6. Here, one simple attack is a SYN flood, which can be generated like per packet. And in case a botnet is able to establish TCP connections. Then there's a long list of possible attacks towards TCP or TLS, like TCP connection flood, SOC stress, and others. And also for TLS, there are also handshake-based attacks. Probably the main issue about IoT is that it can do this. So, by the way, yes, here is a SYN flood, which can affect multiple layers at once. So, in case you face a SYN flood in a real network, you probably want to first not to start with like packet structure analysis or SYN cookies. You probably want to first discover whether it affects your bandwidth or capabilities of an end server. Because most of the time, it's not the bandwidth, it's just the end server, like a Windows server, which isn't able to handle the TCP part of SYN flood. So probably the main issue with IT was not the bandwidth of attacks, because we know long before that such attacks would be possible in future, but the ability to implement full TCP, GRE, or even HTTP flooding. On a scale possible for an average camera or router-based IoT botnet. So this is when this is where the IoT threat was most harmful. It wasn't just a simple packet-based attack. It could do complex transport and even application layer attacks. In terms of mitigation for a SYN flood, you have three-way handshake built into TCP. So you can use the mechanism called SYN cookies and a mechanism built on top of it called SYN proxy, which allows you as a victim to verify the source IP address. Then after that, after the IP address is verified, you can use blacklists or whitelists to manage the access to your network. It's important that it's dangerous to use blacklists or whitelists without source IP address verification. If it's spoofed, you will just end with 4 billion of IP addresses in your blacklist, like the full IPv4 address space. And when you can use blacklists or whitelists, you need some tools which will populate those lists. So you can do other handshakes for other protocols, but on top of it, you always want to use session analysis, also heuristics, in case a TCP connection doesn't go as expected. And it happens like a lot of times. You probably want to look into it and maybe even add those IP addresses to a block list. And also maybe some, not maybe, but always some monitoring to know what's happening there. So going to the yes, so IPv6, yeah, sorry. So in IPv6 has come, and with IPv6 it's possible to address each atom on the Earth surface multiple times, which is good. However, which is bad, you can't store, it was possible to store the whole IPv4 address space in a random access memory of one network server. However, with IPv6, this is totally impossible and won't be possible in future. So about like 10 years ago, blacklisting whole IPv4 networks based on anything, GeoIP database or real attack. However, blacklisting whole IPv4 networks in any case was already considered a bad practice. With IPv6, we have no other way than to revive this method. and if there's a lot of IP addresses coming from a single network and doing some harmful for your network, you'll probably want to blacklist whole IPv6 network. Yeah, it's also possible that there's just one compromised node which just enumerates IPv6 addresses, so we have no other way than to filter IPv6 with whole networks in case of a real attack. So this is transport layer. The next one is, of course, application layer and application-specific flood, which is different for each application. One simple and popular example of a layer 7 attack is the WordPress pingback. During pingback DDoS, an attacker forces a vulnerable WordPress installation to issue HTTP or HTTPS requests towards a victim. With literally millions of those installations available in the world, on the internet, an arbitrary attacker is practically capable of generating a few gigabits of just syn TCP segments using this method. This is about 6 gigabits of an attack traffic when all the sources, all the WordPress servers participating in the attack were actually blocked. They were in a blacklist, so no sessions coming on, just syn segments. In case the attack is not handled with blacklists and WordPress servers are actually able to open connections and issue requests, it's up to a few dozen gigabits of a total attack. Remember the issue with amplification without a fixed source port. As the WordPress installation starts a new request itself each time, the source port is always different, and flow spec is of no help to us. In case of a TLS-enabled resource, the only information enough to reliably tell a WordPress server from a legitimate user is encrypted. Another example of a layer 7 attack is what we call a full browser stack. So a bot which is located like on a user's computer or phone can actually be more clever than a WordPress machine. It can actually use a headless browser instance like Chrome or Internet Explorer or Edge in more recent installations, and use a full stack of browser available to handle JavaScript challenges, HTTP redirects, and other methods used often to deal with simple botnets. So a full browser stack enabled bot is enabled to interact with layer 7 HTTP server. The weapon of last resort against full browser stack is CAPTCHA, which is easy to implement. And generally it works because a browser isn't still capable of solving CAPTCHA challenges. However, sometimes CAPTCHAs are even harder for humans than for robots. In case of far away regions, there are people who don't know like English or don't know what house means in English language. This is the issue with reCAPTCHA. Also, not all bots are malicious and not all humans are innocent. There are human-based attacks where a lot of people just want some server to go down and they just can go through all the challenges. Also, there are CAPTCHA farms like Antigate, and which actually Antigate is actually automated humans. You can put like $1 into Antigate and it will solve like 1,000 CAPTCHAs for you. using people in faraway regions of Earth. Also, the next generation issue with CAPTCHA, sorry, is that image recognition tools evolve fast, and in case your CAPTCHA is provided with handy tools like voice instead of image, which comes handy for a lot of users in the world. Voice recognition tools evolve even faster than image recognition. Also, a CAPTCHA is a nice example of security by obscurity technique, because if a CAPTCHA is open sourced, it is relatively easy to break it using open sourced machine learning tools. This is how you do it. If it's open sourced, you can generate a lot of sample images, like millions of images, and then you can use machine learning tools to build a code which learns about those images. So you know the source, you know the solution for a CAPTCHA. You have an image which corresponds to that solution. You have millions of those. So you can educate an algorithm based on this. There's a link. I believe this is somebody who have done this first for the most popular WordPress CAPTCHA. Another issue with CAPTCHA, which is not present on this slide, is that a bot which is located on a full browser stack enabled machine with Internet Explorer or Chrome. This machine is probably just in front of some human sitting before it, and a bot, a malicious piece of code, can just put the CAPTCHA in the payload of other website to make sure that a human which is sitting on a compromised machine won't notice any differences and will just solve that CAPTCHA for a bot to be able to go past the CAPTCHA check towards an attacked resource. So the idea with CAPTCHA is that it is more like 80/20 principles. You solve 80% of problems with 20% of effort, and after that you still have some issues in case of real-world scenarios. Another example of a layer 7 attack. Okay. So the last note about full browser stack is that under most conditions, such attacks won't cause a link degradation. They will cause computational resources exhaustion on the endpoint. So generally, they must be out of scope of a network operator's responsibility, and it's up for a customer to handle those, except for maybe cloud infrastructures, when you will have processor time and memory degrading for the whole physical machine. But for a physical based not cloud data centers or also network operators, application attacks are mostly out of scope, except for one case when it comes to DNS. So DNS is built on top of UDP. There's an asterisk which is there to remind me that under certain conditions DNS is able to work on top of TCP or TLS or HTTPS, but most of the time in most of the scenarios DNS is using UDP, and DNS request feeds in a packet. And the structure of a DNS query is also simple. This is all you need to do to issue a request for an IP address of facebook.com. So the payload is simple. As a result, an attacker is capable of generating spoofed queries at a almost line rate, which will make a user space DNS application process all those fake requests, rendering a DNS server unavailable in terms of layer 7. So bandwidth more or less works. The server probably works for other applications, but a DNS server will have to handle all those requests in a user space. One example of this is what actually happened in October 2016 with Dyn. The attack is always recognized as water torture. Basically, in a nutshell, it's when a lot of specifically crafted DNS packets, but containing legitimate DNS requests, are issued towards a DNS server in a way that will take it that will make it not use its built-in DNS cache. So basically, there are other methods available for an attacker if they want to bring down a DNS server. Luckily, a DNS protocol in most of the cases allows switching. No, the protocol allows switching to TCP, and most servers enable you to do this. What's most important that almost all clients on the internet, except for some specific cases about like IoT or something, but main end user applications and operating systems allows switching DNS from UDP to TCP. And in TCP, we have a handshake to verify the source IP address. With these, blacklists finally apply to a service. However, you need enough bandwidth and inspection power to handle DNS requests, and you need to be able to do this TCP switching, so DNS truncating, also at a line rate and on a bandwidth of a few hundred gigabits, I believe. So as we've discussed before, DNS allows switching to TCP. Unfortunately, other UDP-based protocols like gaming are mostly built without distributed denial of service mitigation in mind. And in a general case, it's impossible to handle any attack towards that. It's sometimes possible to do some packet analysis in case an attacker is lazy and doesn't generate a correct payload, but in case a payload of a UDP application is correct, you can't do anything about it. That's a problem with protecting gaming and mitigating DDoS attacks towards gaming, that they don't have any built-in mechanisms to handle this. And if you are going to design your own UDP-based protocol, you have to cover this as well. So, this is a classification which was always mutually exclusive and collectively exhaustive, because if a network fails to work, it fails to work on some network layer. And this is all the attacks which are possible for each network layer, so probably this is all you need to care about, except for that case that the internet is a complex thing. There's a decades-old interview quiz, which is most of the time it's expressed like this. So the question is, what happens when you type www.google.com in your browser? There's a GitHub repo which enumerates everything what's going on, starting with interrupts and going down to event handling and then to DNS and then to network. Basically, this is what happens in terms of network handling. So first it's DNS lookup, then socket opens, then the handshake goes through, then the HTTP protocol starts to do something, and then the server just handles the request. At least this is how it was supposed to work 10 years ago, because now you have just a lot of other things to do. It goes through your network connection probably goes through some packet inspection tools. In case of TLS, it's supposed to use CRL or OCSP. There are probably some load balancers before the end HTTP server, and there's always CDN. So as the incident with Dyn shows, an application server could not only be a direct target of a DDoS attack, but each step could suffer from an attack in this list, and could suffer from layer 2 to layer 7. This is one lesson from Dyn attack. If you are going to defend your network infrastructure from DDoS attacks, you need to start with inventory management to enumerate all the dependent services like CDNs or DNS or TLS related things like OCSP or others, to make sure that they won't go down at once in case of an attack. Also, the second thing is infrastructure monitoring, not only for your services, but also for network services your infrastructure depends on. Basically, security is not like a product. It's not an appliance you can buy and forget about it. The security is a process. The ability of DDoS mitigation must be built into the design of a protocol. We've talked about it before. But the main thing is that a concerned company must follow policies. We are not speaking of updates, because we hope that anyone is now ready to push updates towards their network infrastructure, towards operating systems and appliances and network devices. But there are also things like risk management and proper incident handling. A concerned company must develop policies to do something in case this happens, and to follow these policies in case of a real incident. For an average ISP, the risk management is basically limited to bandwidth consuming attacks. However, in real world scenario, an attacker will most likely use just the tool they have at their disposal, like IoT or Windows-based botnet. They won't care about it. They would just use the tool they have at their disposal. Thus, the probability of an attack towards a network is probably the aggregate probability of an attack for each customer in the network. We don't care about on which layer it will go, because it's not up to the customer to decide. Yeah, so this is what I want to talk at the end of the presentation, that memcached was disclosed in November 2017, and 3 months after that, memcached was already in the wild, and 3 months are an overly short interval. Next time it might be even shorter. I have an actual case of Cisco Smart Install vulnerabilities, which were discovered a year ago. Then Cisco was patching for a year. Then they were published, and 2 weeks after that, we've seen attacks towards Cisco Smart Install, flushing all the configuration of exposed network device in the wild. About 2 or 3 weeks after the update was published. So next time, the interval may be even shorter, and as Meltdown or Spectre shows, the embargo approach, when you disclose the vulnerability only among a few entities, does work, but has limited application because it doesn't work well for a community large enough. In case of Meltdown and Spectre, the embargo was broken 6 days before the original date, and if a community is large enough, like a community of network operators, the interval may be even shorter. So probably at this point, it's important to think about how network operators collaborate with each other. How do they react? You cannot call it CRT or CSRT because those terms are were heavily marketed throughout last 20 years, and there's a strong objection about calling anything CRT. But no matter the name, for a strong community, it's important to develop some policies. What are we going to do in case of next memcached or next IoT? To find something to develop some policies. How do we react, and how do we handle this, and what are we going to do in case a new threat is emerged? I invite you to think about it and to discuss it, and maybe to find some ideas, maybe more clever than I do. So, yes, it's not 1.5 hours, but almost. So if you have any questions, it's time for them. Also, there's a Telegram chat, t.me/csnog, and you can post some questions to that. I'm able to read it, and I can answer those. Any questions?
Okay, just in case, just for the process, if you have a question, you should go to these mics that are in the front of the room, state your name and
there's also
affiliation.
There's also a translation, I believe, so you can
yes,
ask
you can also ask in Czech. We will try to interpret it. If you můžete se také ptát česky, pokud by byl problém s angličtinou.
Good. So 3, 2, 1. Okay. Thank you very much.
Thank you, Artem.